Alright guys, in this video we're going to talk about how to estimate a population mean. But before talking about this section, let's take a quick review on what we learned in the previous video, because it's going to help us to understand this section. In last video we learned how to estimate population proportion. In other words, we learned how to construct a confidence interval for the population proportion P. We know that that will be equal to the P hat, which is the point estimate of the population proportion, plus and minus the margin of error. The margin of error is equal to Z sub half alpha times the standard deviation of the P hat. Of course, the formula given in the previous slides or in the textbook doesn't look like this, because but they are equivalent, because we know that the margin of error is let me clean this. First of all, let me show you what the formula looks like in the previous slides. So the formula in the previous slides, I will just put an equal sign here. Okay, they are completely equivalent to each other. P hat plus or minus Z sub half alpha multiplied by square root of P hat times 1 minus P hat over N. And we know that the standard deviation sigma P hat is equal to square root of P hat 1 minus P hat and then over N. That's why I use the sigma P hat over here instead of this whole thing, because they are completely equivalent to each other. So just keep this idea in your mind. The margin of error and the margin of error E is equal to the Z sub half alpha multiplied by the standard deviation of P hat. Okay, that's the definition of margin of error. And we know that the confidence interval, the lower bound of the confidence interval would be, equal to P hat minus the margin of error, which is Z sub half alpha times the standard deviation of P hat. And of course, the upper bound would be equal to the P hat plus the margin of error, which is Z sub half alpha multiplied by the standard deviation of the sigma sub P hat. Okay, that's what we learned from the section 7.1. And there's another point I would like to mention, which is what we learned in the lecture video of 6.1. So in that video, we learned that if we have a random variable x follows a normal distribution, let's say mu and sigma square. That's a normal distribution. The population mean is mu and the population variance is sigma squared. Then x bar is gonna follow the normal distribution as well, which mean mu, but the variance is gonna be sigma squared over N. And we prove this in the video of lecture 6.1. If you are not familiar with this, please check that out. And of course, if we know the variance of x bar is equal to sigma squared over N. Of course, sigma squared is the variance of the population. Okay, here. Once we know the variance sigma squared, the variance is the sigma squared over N, then the standard deviation sub x bar is going to be equal to the square root of the variance, which is sigma squared over N, and this is equal to sigma over square root of N. Okay, in other words, if we want to standardize this thing, so technically if we want to standardize x like this, we know that Z is going to be equal to x minus mu over sigma, right? That's how we standardize the x, which is normally distributed with population mean is equal to mu and the standard deviation sigma. But in this case, if we want to standardize this random variable x bar, then the Z sub x bar would be equal to, of course, x bar minus the mean is mu as well, divided by the new standard deviation. The standard deviation of x bar is this guy here, the sigma over square root of N. Okay, this is how we standardize whatever x. If we standardize x, we got Z is equal to x minus mu over sigma. If you want standardize x bar, the way we got z sub x bar is going to be equal to x bar minus mu all over a sigma over square root of n. Okay, because x bar follows a normal distribution with population mean mu and the variance sigma squared over n. Okay, if you are not familiar with the stuff on the right hand side, please check out the video, the lecture video 7.1. If you are not familiar to the stuff on the right hand side, please check out the lecture video of 6.1. Okay, once this is clear, let's move forward. Let's take a look at how to estimate the population mean. First of all, of course, a very similar idea over here. If we wanna construct a confidence interval, let's for the idea is very similar. If we want to construct a confidence interval for the population mean, then that would be point estimate x bar plus or minus z sub half alpha times I will use in a general form. Okay, so the confidence interval would be the point estimate plus or minus the margin of error E. Okay, this is a very original form. So of course, if we want to construct confidence interval, first of all, we want to find the point estimate. Okay, and we know based on what we learned in 6.1, we know that point estimate is the value of the statistic. It's the value of the point estimator, and we know the point estimator of the population mean is the simple mean. So the point estimate in this case is going to be the value of the simple mean, which is x bar. Now let's take a look at this definition here. A point estimate is the value of a statistic that estimates the value of the parameter. For example, the simple mean x bar is a point estimate of the population mean mu. So of course, the value of x bar is called the point estimate, and x bar itself is called the point estimator of the population mean mu. Okay? But anyway, in this case, we're going to have x bar plus or minus margin of error E. Okay, let's take a look at it. Once this is clear, let's take a look at this example. And I think this is quite straightforward because this is an example for computing the point estimate. It says the pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. The following data represent the weights in grams of 17 randomly selected pennies minted after 1982. So we get 17 numbers here in total. And the problem says treat the data as a simple random sample, estimate the population mean weight of pennies minted after 1982. So if we want to estimate the population mean, first of all, we want to find the point estimate, which is x bar, right? So if we want to find x bar, so we know that x bar is equal to sum of all x values divided by the sample size. So in this case, the sample size is 17, and if we want to find x bar, we just need to add all the x values together and divide by 17. That's pretty much what is done here. The simple mean is x bar is equal to, on the top, we add all the numbers in the data set together and then divided by the sample size n. So this is approximately equal to 2.464. So I wouldn't go over the calculation here because if you have a calculator, you just type the whole thing in a calculator, you get the answer. And then of course, the point estimate of the population mean mu is 2.464. But what we got is just a point estimate. It's not the value of the population mean mu, right? That's why we are estimating the population mean. So as what I mentioned in the previous lecture video, So based on what I mentioned in the previous lecture video, I said that once we have the point estimate, we are not able to say that, okay, we are 100% sure that the population mean mu is equal to that. We cannot do that because we're not sure. We're not 100% sure. We cannot say that we're 100% sure to make a prediction. But what we are able to say that maybe we are able to say that, okay, we are 95% sure that the population mean would be in an interval. So this brings us to the idea of the confidence interval. And we know that if we want to find the confidence interval, so we know the confidence interval for mu is x bar, which is the point estimate, plus or minus the margin of error, right? And we know the margin of error is equal to z half alpha multiplied by the standard deviation of x bar. And we know the standard deviation of x bar is equal to the population standard deviation of x divided by square root of n. Right? That's what we got up here. This is based on what we got up here, okay? This is the sample standard deviation of x bar, and that's why we have that the sigma over square root of n over here, because that's a sample standard deviation of x bar. So once this is clear, let's just take a look at this definition here. This is pretty much the same thing as what we just went over. Definition says 100 times 1 minus alpha percent confidence interval for the mean mu of a normal population when the value of sigma is known is given by that. Okay, it's given by that. If we know the value of the population standard deviation, we just need to apply this formula. Okay, x bar minus z sub half of times sigma over square root of n. So this is the lower bound, this is the upper bound. So basically, equivalently by x bar plus or minus the margin of error. Okay. Of course, once we know alpha, and we can figure out half alpha. Once we figure out half alpha, we can find the corresponding z squared z sub half alpha. Right. So by now everything looks good and it works well. But there is one problem. There is only one problem. The problem says when the value of sigma is known. What if the value of the population standard deviation is not given? We gotta calculate it, right? So if we want to calculate it, let's see what we need. What do we need? The population standard deviation, the sigma, is equal to the square root of sum of xi minus mu squared divided by n, the population size. That's the original formula of population standard deviation. Let's say, what do we need? We need the population mu here, right? We need the population, we need the population mean here. But what we're doing here, we are estimating the population mean, right? We're estimating the population mean, which means there's no way we know the value of the mu here. If we know the mu, we don't have to do the whole thing here, right? If we know the mu, we don't have to estimate it at all. Okay? Then what are we going to do? We're gonna talk about two different situations. Number one, if n is sufficiently large. If n is sufficiently large, the standardized variable, we know that x bar follows normal distribution with population mean mu and the variance sigma squared over square root of n. Of course, if we want to standardize this x bar, the z would be equal to x bar minus mu. This mu is coming from here, divided by the standard deviation, which is sigma over square root of n, right? But if we don't know the value of sigma and n is sufficiently large, we're gonna replace the sigma with the simple standard deviation here. So in this case, z is equal to x bar minus mu over x over s. I'm sorry about that. Let's do this again. Z is equal to x bar minus mu all over the simple standard deviation divided by square root of n. And this standardized variable has approximately standard normal distribution. This implies that the confidence interval would be equal to x plus minus this margin of error. So in this case, we use the sample standard deviation on the top here instead of population standard deviation. So this implies that this thing is a large sample confidence interval for mu with confidence level approximately 100 times 1 minus alpha 100%. This formula is valid regardless the shape of the population distribution. So basically, if we have n is sufficiently large, we don't have to worry about the distribution of population. We can just go ahead to apply this formula, okay? Because once n is large enough and the data is given, we can calculate the x bar and we can calculate the simple standard deviation. Of course, if the level of confidence is given, we can find out alpha. Once we can find alpha, we can find the z sub half alpha. Once we get all of those numbers, we plug back into here, we will get the confidence interval for mu, right? We can get the confidence interval for the population mean, which is mu. But what does it mean by saying n is sufficiently large? What does it mean? That means, generally speaking, n greater than 40 will be sufficient to justify the use of this interval. This is somewhat more conservative than the rule of thumb for the CLT. This is a central limit theorem because of the additional variability introduced by using S in place of sigma. So what does it mean? If you wanna construct a confidence interval for mu, first of all, you wanna say the sample size. Oh, I'm sorry. You wanna say the sample size. Case 1. Sample size. Sample size is greater than 40. So once this happens, once we have the sample size is 40, then the confidence interval would be x bar plus or minus z sub half alpha times the little s over square root of n. Okay? Why we have z sub half okay, I think there's one point I forgot to explain why this is a z sub half alpha over here. It is because that this whole thing is normally distributed. This whole thing follows the standard normal distribution. Okay, because we can do the process of standardizing the variable x bar, and we have this whole thing follows the standard normal distribution. If we have this whole thing here follows a standard normal distribution, we're going to use z sub half over here. Okay, that's for n is greater than 40. Okay, so basically, if you read the question and you see, okay, you are constructing the confidence interval for the population mean, and we know n is greater than 40, so you just apply this formula here. Okay, we just apply this formula here. And then case 2, n is less than or equal to 40. If n is less than or equal to 40, first of all, we have that once again, the process of standardizing would be x bar minus mu divided by the sample standard deviation over square root of n, right? So if n is not large enough, we cannot replace sigma by little s here because they are not equal. So when n is very large, when n is going to be infinity, we have that the sample standard deviation is going to be getting closer to the population standard deviation. So in other words, if we have n is greater than 40, we can just use the sample standard deviation to replace the population standard deviation sigma. But if n is less than 40, we cannot do that. Because different samples will give us different sample standard deviation. So that means the sample standard deviation itself changes. It's a variable. Okay? It's variable. So this whole thing is not normally distributed not anymore. It's not a standard normal distribution. And we have a new distribution for that. This is called t-distribution. Okay? First of all, we have that the n is less than or equal to 40, and we have x is get rid of that. X is a normal distribution with population mean mu and variance sigma square. If we have those two conditions, and where we want to construct a confidence interval for the population mean, we have this thing here. This is a standardized variable, follows the t-distribution. Okay? I wish you have a good understanding on it, because we're going to see this a lot in chapter 8 as well. Now, let's take a look. Once this is clear, let's take a look at this t-distribution here. Suppose that a random sample of size n is taken from the population. If the population from which the sample is drawn follows normal distribution, so the population follows normal distribution, and the distribution of t is equal to x bar minus mu all over s over square root of n, follow students t-distribution with a -1 degrees freedom, where x bar is the sample mean and the little s is sample standard deviation. So just keep the idea in your mind. First of all, your sample size is small, which means the sample size is less than or equal to 40. That's number one. Number two, the population follows normal distribution. And then once we have those two conditions, we're going to see this whole thing follows a t-distribution with degrees of freedom n minus 1. So this is a t n minus 1. This is degrees freedom, okay? And just always keep this idea in your mind. The degrees freedom of a t-distribution is always n minus 1. Always n minus 1, okay? I believe I explained the degrees freedom in one of the lecture videos of chapter 1. You can check that out. I wouldn't explain too much about it over here. Just keep the idea in your mind. The degrees freedom of a t-distribution is n minus 1. Of course, n is sample size. N is sample size, okay? Now, once we know the definition of t-distribution, let's take a look at the difference between the standard normal distribution and the t-distribution. Obtain 1,000 simple random samples of size n is equal to 5 from normal population with mu 50, population standard deviation is 10. Determine the sample mean and sample standard deviation for each of the samples. So since sample size is 5, right? And we have 1,000 samples. So the as what I mentioned before, 1,000 different samples will give us 1,000 different sample standard deviations. Now let's take a look at the difference between this standard normal distribution and this t-distribution. So this graph is the histogram for z. So now we can tell that it's symmetric around 0, and this is pretty much from -3 to +3, something like that. Because we know that so based on the empirical rule, we know that 99.7% of data will between mu minus 3 standard deviation and mu plus 3 standard deviation. This is the empirical rule we went over before, right? Now this is the histogram for z. Now this is a histogram for t. Now we can tell for this one actually is centered at 0 as well, and is symmetric around 0. But the difference between the t and z is that the t is more spread out. It's more spread out. I will draw this. So we can tell the t is more spread out. The t get longer tails than the z, and that's the main difference between z and t. Because so what make the longer tails in t is this little s over here. The little sample standard deviation is a variable itself, okay, because it changes from sample to sample. So this variable here makes the t distribution more variable than the z over here. Okay, Now let's take a look at the conclusion here. The histogram for Z is symmetric and bell-shaped with center of distribution at 0 and virtually all the rectangles between -3 and +3. In other words, Z follows a standard normal distribution. So this is pretty much the same as what we went over in a previous video about the standard normal distribution. Now let's take a look at the conclusion about the T. The histogram for T is also symmetric and bell-shaped with the center of the distribution at 0. But the distribution of T has longer tails, which means this is more dispersed. So it is unlikely that T follows a standard normal distribution. The additional spread in the distribution of T can be attributed to the fact that we use S to find T instead of sigma, because the sample standard deviation itself is a random variable, okay? Rather than a constant such as the population standard, because the population standard deviation is constant, we have more dispersion in the distribution of T, and that's why. And this little thing, this little sample standard deviation, is why we have more dispersion in the distribution of T, because the little s, the sample standard deviation, is a random variable as well. Okay. All right, once this clear, let's just take a look at the properties of T distribution. Okay, it's kind of similar to the properties of the normal distribution, but there's one difference is degrees freedom. The T distribution is different for different degrees freedom, and just always keep the idea in your mind. Degrees freedom of T distribution is always n-1, and the T distribution is centered at 0 and symmetric about 0. And number 3, the area under the curve is 1. And the area and the curve to the right of 0 equals the area under the curve to the left of 0, which equals 1/2. As T increases or decreases without bound, the graph approaches but never equals 0. So we can say that based on the graph we have here, of course, this is not so very accurate. So it's something like this. But anyway, it should be approaching to 0 infinitely, but will never touch. Okay. So once we got that, let's take a look at number 5. The area in the tails of T distribution is little greater than the area in the tails of the standard normal distribution, because we're using the sample standard deviation as an estimate of the population standard deviation, thereby introducing further variability to the T statistic. So this thing makes the T distribution not stable as the normal distribution. Number 6, as the sample size n increases, the density curve of T gets closer to the standard normal curve. This result occurs because as the sample size n increases, the value of S getting closer to the value of sigma by the law of large numbers. So basically, as n increase getting to infinity, we have that the sample standard deviation is getting closer to population standard deviation. So basically, in other words, if n is large enough, excuse me, if n is large enough, then we say we can use the sample standard deviation to replace the population standard deviation. To say n is sufficiently large means that n is greater than 40. Okay. So basically, if n is greater than 40, we use Z. If n is less than or equal to 40, we're going to use T. Okay. Now let's take a look at this graph over here. This is pretty much the relationship between T and Z. So the very top blue one is for Z as for normal distribution, and the bottom two are for T. So now we can tell that of course the very bottom one is for n is equal to 5. The middle one is for n is equal to 15. So that means that when n increases, the T distribution is getting closer to a normal distribution, and that's why. Because when n increases, the sample standard deviation is getting closer to the population standard deviation. And then let's take a look at the notation. The notation T sub alpha is the T value such that the area under the standard normal curve to the right is alpha. The figure illustrates the notation. So I'm not sure if you are remember or not, if you don't, please make sure you understand it. This notation z sub half of sub alpha, whatever, sub alpha, sub half alpha. So this notation means that if we have a normal curve here and this is a z sub alpha, so that means the area to the right of this z-score is alpha. Okay, that's a special notation. So similarly, the t sub alpha over here, that means the area to the right of this t-score is equal to alpha as well. Okay, that's the special notation here. And then I'm gonna show you how to find the corresponding t-value. Of course, when we're looking for a z-value, we got z-table, and if we are looking for a t-value, we're gonna have a t-value. Now, if we want to find a t-value, we're gonna need a t-table. Okay. So the problem says find the t-value such that the area and the t-distribution to the right of the t-value is 0.2, assuming the 10 is degrees freedom. That is, find the t sub 0.2 with 10 degrees freedom. So you gotta really watch out that if the problem gives you a degrees freedom directly, or it gives you the sample size. If it gave you a sample size minus 1 is the degrees freedom. But if the problem gives you the degrees freedom directly, we can use that over here directly. Now let's take a look at the t-table. Here's the t-table. So we can tell that the first row is I'm not sure. Give me 1 second because it doesn't work very well. Let me use another one. There it is. For some reason, I cannot make a comment on it. It doesn't work at all. But anyway, we have the first row represents the degrees freedom. No, the first row represents the area in the right tail, and the first column represents the degrees freedom. Now, keep this idea in your mind. The first row means the area in the right tail. That's the difference between the t-table and z-table. In z-table, we need the area to the left. Okay, but in the t-table, we need the area to the right. And we're looking for the t-value with the area to the right is 0.2 and degrees freedom is 10. So it's over here 0.2 and 10 is over here. For some reason, I cannot make comments, but you can tell the intersection part 0.2 with the 0.2 for the area in the rectangle and degrees freedom is 10 is 0.879. Once again, area in the rectangle is 0.2 and degrees freedom is 10. Okay, and the area, the intersection part, which is the t-value, equals 0.879. 0.879. For some reason, I cannot make the comment in it, but I think it's pretty straightforward. Okay, now let's get back to the notes. So basically, this is solution here. It says the unknown value of t is labeled, and the area and the curve to the right of t is shaded, which is this part over here, and the value of t sub 0.2 with 10 degrees freedom is 0.879. That's the exactly same thing as what we got from the t-table. Okay. All right, now let's take a look at the conditions for constructing the confidence interval for the mu. Sample data come from a simple random sample randomized experiment. A sample size is small relative to the population size, so we don't have technically we need to, but in this class we all the problems we meet in this class, always satisfy this condition. The data come from a population that is normally distributed or the sample size is large. So basically, that's the two different situations we made before. So if we want to construct a confidence interval for the population mean mu, we're going to have two different cases to consider, right? So for case 1, n is greater than 40, greater than, not greater than, equal to, n is greater than 40, then we're going to have the lower bound is equal to x bar minus z sub half alpha times the simple standard deviation over square root of n. And of course, the upper bound would be equal to x bar plus z sub half alpha times the standard deviation, simple standard deviation divided by square root of n. Case 2, n is less than or equal to 40. Okay? In this case, the lower bound would be x minus t sub half alpha times the simple standard deviation over n. Okay? Because in this case, if n is not sufficiently large, the standardized random variable follows a t distribution. Of course, the upper bound would be x bar plus t sub half alpha times the simple standard deviation over square root of n. That's pretty much the two different cases we want to consider if we are looking for a confidence interval for the population mean. Okay, so the very first thing you want to say if the sample size is greater than 40 or not. Okay, so that's pretty much the same thing as what we just went over. So a 1 minus alpha 100% confidence interval for mu is given by lower bound, of course in this case n is less than equal to 40. Lower bound x bar minus t sub half alpha times the simple standard deviation over square root of n. Upper bound would be x bar plus t sub half alpha and simple standard deviation divided by square root of n. And where t sub half alpha is a critical value with a minus 1 degrees freedom, and of course you can always get the t value from the t table. Okay. Now let's take a look at this example again. So construct 99% confidence interval about the population mean weight of pennies minted after 92. So actually of course we want to find the point estimate first. I think I'll just in this case since n is equal to 17, which is less than 40, so we want to consider the case 2 here, so which means it follows a t distribution. Now let's take a look at what we did here. We know that the alpha is equal to 1 minus the level of confidence. So in this case that would be 1 minus 99%, which is 1%, which is 0.01. Okay, 1% is 0.01. So of course, half alpha would be 0.01 over 2, which is 0.005. And the degrees freedom is minus 1. We know the sample size is 17. Minus 1 is 16, right? So we're looking for the critical t value with critical t sub. We are looking for t sub 0.005 with degrees freedom is 16. Of course, we can find this t value from the t table. If you go to the t table, let me see. Of course, I know I can not make any comment on it, but I still like to show you how it looks like. Let me see if I can convert it to a PDF or not. No, I cannot do that. But anyway, so we know that the area in the rectangle is 0.005. So we go to find 0.005 from the first row. And we know the degrees freedom is 16. And then we find 16 from the first column. And the intersection part for degrees freedom is 16 and 0.005 from the row is going to be 2.921. I believe you can locate this value by yourself as well, because I have already told you that the degrees freedom and the area in the rectangle. So the t value is 2.921. Now let's get back to the not this one. maybe this one? No, this one. Yeah, there it is. Now we have the t-value is 2.921. So that's what we get from the t-table, and we know x bar is 2.464, right? That's what we get from the very beginning of the slide of this section. So of course this is equal to sum of all x values over n, which is 17. Okay, and of course we can find both the simple mean x bar and the simple standard deviation from the calculator. But if you want to figure it by hand, we know that the simple standard deviation is equal to sum of xi minus x bar squared all over n minus 1. So if you want to calculate it by hand, don't forget you got divided by n minus 1 for the simple standard deviation. And of course you can get both x bar and simple standard deviation from calculator as well. So in this case, we have that the x bar is 2.464 and the simple standard deviation is 0.02. And we have the t-value is 2.921 and we have the sample size is 17. So we plug all of them back into this formula to get the lower bound, which is 2.45. And of course, same thing, we plug all the numbers back into this upper bound. We get the upper bound is 2.478. And then we can just go ahead to make the conclusion. We say that we are 99% confident that the mean weight of pennies minted after 1982 is between 2.45 and 2.478 if you want to round it to 3 decimal places. So basically, if the problem, of course, we can find this confidence interval from the calculator as well, and I'm gonna make a video for that. You can check that out on Canvas under the media gallery. But if the problem asking for your work to get a full credits, and that's pretty much the whole thing you want to show me, okay? And of course, you got to say that there is something need to be added. That's 99% confidence interval is 2.450 and 2.478. Okay, that's all the work you need to show me to get the full credits. So okay, once this is clear, and sometimes the margin of error is given, and we want to find out the corresponding sample size by doing some calculation. We know that margin of error in this case E is equal to t sub half of times s over square root of n, right? So same thing, if we want to solve for n, we just need to go, first of all, we divide t value by both sides equation. E divided by t sub half of is equal to s over square root of n, right? And then we want to multiply by square root of n, to move, to get rid of the square root of n from the bottom of fraction. So we're going to have square root of n is times e over t sub half alpha is equal to the simple standard deviation. And then we isolate the n term. Square root of n is equal to s divided by this fraction here. So we're going to multiply by the reciprocal of it. So we put the t sub half alpha on the top and then divided by e. And then we square it. And n is equal to s times t sub half alpha over e, and then square. Now, what's the problem over here? The problem over here, we need the t. We are looking for the n, the sample size n, but what we need is the t value. But we know that if we don't have n, we don't have n minus 1, which is degrees freedom. Which means if we don't know the sample size, there's just no way we're gonna have that the corresponding t value here. So we cannot find t value. But we're gonna use z sub half alpha to replace the t sub half alpha over here. Okay, to get approximate sample size we need. So basically the formula for the sample size n is the quantity squared of z sub half times the sample standard deviation all over the margin of error. And of course you gotta round it up to the nearest whole number. So basically, once you know the excuse me, once you know this formula, so what we need to do, just plug and play. Now let's take a look at this example here. Back to the previous example, how large a sample would be required to estimate the mean weight of the penny manufactured after 1982 within 0.005 grams with 99% confidence. Assume the simple standard deviation is 0.02. So we have the margin of error here is 0.005. Now we know that we know the formula that n is equal to quantity squared z sub half of times the sample standard deviation over the margin of error. Now we have E is equal to 0.005, right? 0.005, and the sample standard deviation is assumed to be equal to 0.02. And we know alpha is 1 minus 0.99, which is 0.01. Of course, half of alpha would be equal to 0.01. Of course, this is alpha. 0.01 over 2, which is 0.005. So basically, we just need to find z sub half alpha from the z table. Okay? So from the z table, I'm not going to show you again. Over here, if we have the z score, so this is what you can get from the z table, 2.575, and we know the sample standard deviation, and we know the margin of error, and then we just plug those whole three things back into this formula, and we have this is equal to 106.09, and we always round it up, so the n is 107. That's pretty much how to find the required sample size with the given simple standard deviation and the margin of error. Okay, I think that's pretty much all I want to talk about in this section 7.2, and I'm gonna upload the how to use the calculator to construct the confidence interval for the population mean as well later on. And I wish you have a good understanding on it, because especially for the t distribution. I think I will make a summary. I have already done it over here. The two different cases, if you are constructing the confidence interval for the population mean, the two different cases you want to consider. So if n is if you have n is greater than 40, so just use the z. If you have n is less than or equal to 40, you need to use the t value here. All right, I wish you have a good understanding on it, because we will say something about the t distribution in chapter 8 as well. All right, that's pretty much all about this video.